action pairs. So now we've got a new table, a table of our eligibility for each state action pair. Think of this as the thing which is telling you how much credit or blame you should assign to every action you took from every state. Like you end up, at the end of your episode, you get a big carrot at the end of your episode. So which of the states and actions are responsible for that carrot? And your eligibility trace is your best estimate of who was responsible for receiving that carrot. And so what we do again is we say that the states and actions that I took that were most recent before I got the carrot, and the states and actions that I took most frequently along the trajectory are the ones which should be blamed or credited the most for their negative or positive reward that I receive at the end of that trajectory. And so the way we do that then is we can do it online by just increasing this state action pair. So every time we actually visit a state action pair, so if we actually visit it, we increment it. So this is just something that says, this is an indicator saying if I'm actually in that state S and take that state, that action A, then I'm going to increase this eligibility trace by 1. Okay, so if I actually see that particular state action pair, increase my trace, and then every step for all state action pairs, even the ones we don't visit, we're going to decay them a little bit over time. We kind of have this process where, if I'm going around and this is the state that we're really considering here, if I keep going around and every time I revisit this state, I'm going to bump up my eligibility, and over time it's going to decay until I get back there again, and then it's going to bump up again. And then if I receive my carrot, whatever the latest eligibility is, that's how much blame I'll put on that particular state. And so what do we do then? Well, now we've got these eligibility traces, we just update our Q values for every state and every action. We update in proportion to the TD error. That's the event that happens of getting the carrot, or the surprising event where you got more or less reward than you expected. And the credit or blame that you assign is proportional to your eligibility trace. So now the algorithm is to say, let's update our Q values in proportion to the TD error, the difference between what I thought was going to happen and what actually happened, multiplied by this credit assignment trace, this eligibility trace. Yeah, question?
Is there a way to apply this to very large state spaces where you don't effectively ever visit the same space twice, where you're using functional approximation for your value functions?
So the question is, can we do this in very large state spaces where you can't store this table? Next class. Okay. So next class we deal with function approximation. For all of the algorithms we've seen so far, we will generalize to function approximation in the next class. And so the answer is yes, you can do that, and should do that, because table lookup is typically naive, and you can't solve large problems until next class, and then you'll be able to. So Sarsa lambda, it looks something like this. So we're going to basically initialize our eligibility traces to 0 at the beginning of each episode. You want to say, well, I can't blame anything yet, I haven't seen anything. And then for each step of the episode, we take our actions using our policy. We're again on policy here, so we pick our action from our policy, for example, acting epsilon greedily. We compute our TD error, so we look at the difference between the reward plus the Q, the value of the state and action I ended up in, minus compared to my previous estimate. So this is just the one-step error between what I thought the value was going to be before and what I think the value is going to be now. We increment our eligibility trace. We decay all our eligibility traces down here. So here we're just incrementing the state action pair we actually visited, but here we're decaying it for all states and actions. And for all states and actions, not just the one that we visited now, we do an update, because we need to update everything in proportion to its eligibility, not just the thing which we visit at this step. Everything might be blamed now, or credited for what happens. So we need to update all state action pairs. And we update them all in proportion to the TD error and the eligibility trace. And we just iterate every single step. So what does that look like? So I think this hopefully will help to get some flavor of what the difference is between Sarsa lambda and standard Sarsa. So imagine you're in some grid world where you're trying to get from here to this goal state. This could be like the windy grid world we just looked at. And you do some random walk to begin with, and eventually you end up there. Okay? And now let's say that you start off initializing all of your state action values to 0. Okay? And now what we're going to do is indicate the value of those state action pairs by an arrow in the direction of that state action pair, And the size of that arrow indicates how big our Q value is for that particular action. So what would the updates look like? Well, if you just did one-step SARSA, you get to the end here. You started off thinking you had a value function of 0 everywhere. You get to the end and you're like, aha, I actually got a reward of 1 once I reached there. So surprise, now you need to make some updates to adjust the values of your trajectory towards what actually happened. But in SARSA, if we look at the updates which are made at every other step apart from the final one, like here, we thought the value was 0. After this step, we also thought the value was 0, because we initialized all our Q values to 0. So nothing changes here. Over here, we thought the value of going right was 0. We ended up in a state where if you go right, you get a value of 0. So again, nothing changed here. The only place you get a change was in this very final step here, where you thought you were in a situation where if you go north, you got a value of 0, but then you ended up in a situation where you got your caret. So now, this guy will be updated, and you'll end up adjusting this one to say, okay, now you're going to have a very nice positive increment. You're going to increase this value of this action going north to some higher value, and you'll think that this was a good action. Now if you run another trajectory, and you end up coming back through that same action, that will now propagate backwards one further step. So if you were over here now, you start in this situation where you thought the value of going left was 0. You ended up in a value where you're now estimating the value of going north to be something high. So now you would increase the value of this guy. For the value of going west from here, you would increase by some large amount. At the next step, that would propagate backwards. At the next episode, it propagate backwards again. But you need a lot of episodes. You're only propagating the information back by 1 step per episode in SARSA 0. Okay? In SARSA lambda, it looks quite different. So the lambda parameter determines how quickly, how far that information should propagate back through your trajectory. So again, if we consider the same trajectory, you would build up your eligibility all the way along this trajectory. So each of these state action pairs that you visit would have their eligibility trace increased. The first ones would have decayed quite a bit, down towards 0. The ones more recent would have decayed less. And now when you actually see this reward of 1 at the end, you would increase all of those state action pairs in proportion to your eligibility trace. So that means all of them, when you see this surprising positive benefit, all of them get updated in the direction of what actually happened. So this information flows backwards in just one episode, most of the way back towards the beginning of the episode. So you get a much faster flow of information backwards through time by choosing this lambda parameter. So the idea of lambda is so we can say that it basically defeats the tyranny of the time step. That if you have many, many, many time steps, SARSA 0 is always susceptible to the fact that you need more and more steps to actually flow this information back. Whereas using a lambda parameter, you can always just pick your lambda so that information flows back at the right rate, regardless of the granularity that you make your time steps operate at. So lambda basically overcomes this tyranny of the time step. Okay, any questions there before we move on to the final section? Yeah.
You said that the eligibility traces would decay along the path, but
yes.
It would be 1,
No, or so if we go back to the updates and the algorithm, the eligibility trace is incremented in all the states and actions you visit, but it's also decayed every time step. It's decayed by a factor of lambda, and also by your discount factor gamma. So that's why this lambda parameter sets the rate at which how far back in time you look, because now you've got this decay rate, which basically tells you how steeply you want your eligibility trace to decay going back along this trajectory. So if you set lambda to 1, these will be of equal magnitude, like these arrows would still be thick, like the updates that you make all the way along the trajectory would still be large, and that's what happens in Monte Carlo, because in Monte Carlo, you run your trajectory, you see that you get some eventual reward, and everyone gets updated in the direction of that reward, because everyone says, hey, I took this action, I ended up getting something good, I should be updated. So by tuning your lambda, you basically determine how far back along this trajectory you look. It controls your bias variance trade-off. further back you look, the more variance you have, because there are all these random things which happen along this trajectory. But you reduce your bias. You're less susceptible to the effects of bootstrapping. Okay. Question at the back first.
Yeah, I thought you said that for the backward you don't necessarily need to wait until the end of the episode, but here you can do that.
You don't need. Okay. The great question. So the question was, why wait until? So for the backward view, the advantage is supposed to be you don't need to wait until the end of the episode. So we're actually running an update every single step. Now the fact that the reward only occurs at the end of the episode means that you don't actually gain any information until you reach there. So these arrows are basically showing you, by the time you get to the end of the episode, what's the effective update that you see. But the nice thing about, imagine that you pass through this reward and then you carry on, and then you get another reward, and then you get another reward, and then you get another reward. So what would happen with Sasa Lambda is that nothing would happen until you hit your first reward, and then immediately all of these guys would be updated, even though you haven't finished your episode. You would carry on and you would carry on and you would carry on until you hit your next informative event. Then everything would be updated because of that next informative event, and you would carry on and you'd carry on. So the fact that nothing happens isn't because we had to wait until the end, it's because actually that we gained no information until this point. Like until this point we thought the value was 0 everywhere, and we got 0. So we are making updates at every single step, it's just those updates contain 0 information until the first informative event. But you're right, I think this example it's not clear from this example that is really a property of the online algorithm. Okay, there was one more question.
Yeah, so vis-a-vis action values, and over many episodes, we're basically going to be taking the mean of these. So I just want to clarify that.
So in Sasa, we never take an explicit mean. We just use these Sasa updates.
Yeah.
So the updates that we do are precisely the updates that we saw in the algorithm, which are basically updating the Q values a little bit in the direction of So if we see some reward where we thought there wasn't going to be a reward, that generates an error, and we update every value a little bit in the direction of these of our TD error multiplied, our unexpected reward that we got, multiplied by the trace, by the credit that we're assigning to each of those states and actions. That's it. That is the process by which we estimate the mean. So there's no additional step of taking the mean. It's an incremental way to estimate the mean value, if you like, the expected value. But we're not forming explicit mean, and furthermore, we're forming this non-stationary estimate. And actually, that's a point I should make more explicitly, which is if we look at the updates that we make. So we use this fixed step size alpha. So could you just take the mean by using, say, a 1 over n? Like, could we do the same thing that we did in Monte Carlo, where you count the number of times you visited that state action pair and plug in 1 over n as your step size? That would give you like a mean, an incremental way to estimate the mean. But the thing which you're plugging into that mean is changing all the time because you're bootstrapping. So it's not really the same as forming a true mean. You're forming like a non-stationary mean of that. You're throwing in there all of these different targets that you've seen at all these different times. So I think the right answer to your question is that we are forming an estimate of the expected reward, the expected future reward, all the way to the end of the episode. One way to estimate that is using Monte Carlo learning, which explicitly estimates the mean. Another mechanism for estimating that expectation is by bootstrapping, and that's sort of instead of computing the mean, we now update a little bit in the direction of the errors that we see. So we bootstrap, we look at the error, and we use that error to inform what we think the previous value should have been. And that is the process by which we estimate the expectation. Okay. And again, the equivalence between the backward and forward is not obvious, but it is possible to prove. There was a proof in the last lecture, and that proof follows through for the control case as well, roughly. But I think a useful way to understand what's going on is to understand that really what we're doing when we do these traces is to implement this algorithm here. So we're implementing an algorithm in an incremental way, which is basically updating our Q values a little bit in the direction that mixes over our estimates at all these different timescales, where we bootstrap from n steps, from all different n step returns. So you start in some state action pair. So if we go back to this view here, another way to look at this, what would the forward view look like? So forget eligibility traces. The forward view would say, you start at each point in this diagram. Now you really do wait until the end of the episode. That's the forward view. At the end of the episode, from each of these states, we would consider the one-step return, which will give you no information. We'd consider the two-step return, which will give you no information. Consider the three-step return, which will give you no information. And the only one which will give you the information is the longer returns that go all the way to here or beyond. Okay? And the amount that you take account of those things, the weights that we put on that final n, on that largest n, the weight that we put on our final one, is precisely the amount by which we would update that guy here. And so if you're very close to the end here, all of your weight goes on your return, on your final return, because the episode stopped here. Whereas if you're way back at the beginning here, a lot of your weight is going on these shorter returns that don't contain any information yet. And so that gives you the same effective result. You can see just intuitively that just looking at these diagrams, you get the same picture by either this forward view computation or the backward view computation. But the backward view is computationally much nicer. We do that online. You just keep one step in memory. You just do that thing. You move on. You don't need to look forward in time or wait until the end of your episodes. It works in situations where you don't even have episodes.
Can I just ask one quick question about the size of it's just storing the eligibility trace
in
a computer. So is that a kind of matrix which has got two dimensions? One is the number of states, and the other dimension is the number of actions.
Yes.
So
in this lecture, we're building tables for both Q, which is a matrix, number of states times number of actions, and eligibility trace, and the count when we were doing Monte Carlo, this n, s, a. All of these quantities were tables, and the tables were number of states times number of actions in size. You can store that as a matrix, if that's a helpful way to think of it. In the next class, we're going to look at ways to approximate that potentially very large matrix by an arbitrary function approximator with a smaller number of parameters for both Q and also for eligibility traces. Okay, let's change gear a bit. Now we're going to talk about off-policy learning. So everything so far has considered the case of on-policy learning, where the policy which I'm following is the policy that I'm learning about. But there are many cases where we want to consider how to evaluate some other policy while we're following. So let's say we're going to follow some behavior policy that we're going to call mu. So this is the behavior policy that we actually pick actions from in the environment. So mu. And what we want to do is to evaluate some other policy, pi, so as to compute, say, v pi or q pi, or ultimately figure out maybe the optimal way to behave in that environment. But the behavior that we see is not going to be drawn from this thing that we're wondering about. So why would we want to do that? Why do we care about off-policy learning? So here's 4 possible reasons that you might care about this a lot. Okay. The first reason is that you might want to learn from observation of other agents, like humans. You might want to see how humans behave, and not just do supervised learning to copy what the human did, but look at the traces of behavior, look at the episodes of behavior that the human executed, and actually, just from that experience, figure out how to do better, figure out how to solve the MDP just from watching some human, steer some boat around, and then look at what they did and say, I know how you could have done better. You could actually have got more reward by following this other path around. That's the goal. Okay, we want to be able to observe some other policy and maybe figure out how to do better, or learn from that behavior, learn from one behavior what the value of another behavior would be. A specific case, we used this, for example, in the Atari work that I mentioned in the first lecture, is to reuse experience from old policies. So this is a case where, imagine now that we're doing our generalized policy iteration. So we move through a whole sequence of policies when we do that. We start with some initial random policy pi 1, and then we make it a little bit better to give us pi 2. Eventually we end up getting better and better policies. But what if we want to go back over the data that was generated using those old policies and use it more than once instead of just discarding this data, which is very data inefficient? What if we want to go back over it and look again and say, oh, I remember I did this thing, I've seen this state before, when I was last here I did this other action and I got this other reward. Reuse that data, do something a bit more like batch methods where you kind of you just treat this as a big data set and figure out how to do the best thing from that data set. Well, what's the problem there? The problem is that we're trying to evaluate our current policy. And when we're doing policy iteration, we want to know, this is our current policy, we want to know how good that is. But we've generated behavior using all kinds of different policies. So is it possible to make use of this additional data to get a better estimate of the value of this final policy? And the answer is yes, if you use off-policy learning. You can basically just treat this as other behaviors that generated that data, just like the human. This could be, think of this as the human and this is some other robot, and you kind of just want to look at all of that data and figure out from all those other sources of experience how to do better. Probably the best known example of where off-policy learning is used is this third point, which is to say, we know that there's this big issue in reinforcement learning, which is making sure that you explore the state space effectively. At the same time, we want to learn about the optimal behavior, which doesn't explore at all. So why not make use of off-policy learning to generate, and now we can have an arbitrary exploratory policy that just explores around with as much exploration as we want, and at the same time learn about the optimal policy. That requires us to be off-policy. We want to learn about how to behave optimally, something which is ultimately going to be deterministic, whilst following something completely random. Okay? That's another motivation for off-policy learning. And perhaps looking forward, to grander visions, the most exciting reason to care about off-policy learning is we might want to learn about multiple policies while following one. So there might be many different behaviors we want to figure out. I might want to know what will happen if I leave this room. How much reward will I get? Will you guys be pleased or disappointed? I don't know. Maybe I should figure that out whilst carrying on talking to you. But I might also be wondering what would happen if I changed the topic and went back to 3 slides ago. There's all kinds of questions I might be asking about the future, which are conditioned on following different policies. And I want to know what would happen if I followed all of those policies, and I want to learn about them all from one stream. I only get this one stream of data that we call life, and I want to learn about all of these other policies and figure out the answer to all kinds of different conditional questions whilst following that one stream of experience. Okay, these are all reasons to care about off-policy learning. So it's a significant problem, and it's actually a thorny problem for reinforcement learning, as we'll see next class. But we're going to look at 2 mechanisms for dealing with this. The first of which is importance sampling. Oh, I used a lot of time advertising it, so let me talk about this. So the first mechanism is to basically do importance sampling, and the main idea there is to take this expectation. There's some expectation, like your expected future award, and all we do with importance sampling is to say an expectation over your, say, your future award is just to sum over some probabilities times, say, how much reward you got. And now what we can do is just multiply and divide by some other distribution. And now this ratio here that we've got, you can basically say this is an expectation over our other distribution of this quantity here, where all we had to do was kind of divide out our old probability. And basically you multiply and divide by the ratio between your old and your new distributions. And that corrects for the change between your distributions. So we can apply importance sampling to Monte Carlo learning by basically doing importance sampling along the entire trajectory. So when we importance sample across in Monte Carlo, we have to look at the trajectory. We have to multiply these importance sampling ratios across the entire trajectory. Like every single step, there was some action I took according to my behavior policy, and there's some probability that action would have been taken under the behavior I'm actually trying to learn about. And so it kind of, you have to multiply these ratios together, and in general it becomes a vanishingly small probability that the return that you saw under your behavior policy actually matched, gives you any information at all about what would have happened if you followed some completely different behavior. So you can use this idea, but it's extremely high variance, and in practice it's just useless. Okay? So Monte Carlo learning is a really bad idea off policy. It just doesn't work because over many steps your target policy and your behavior policy just never match enough for it to be useful. And so you have to use TD learning when you're working off policy. It becomes imperative to bootstrap. And so the simplest idea to use TD learning is just to importance sample, but you only need to importance sample over one step now, because we're bootstrapping after one step. So all you have to do is basically update your value function a little bit in the direction of your TD target. And the TD target now, all we're going to do is take that TD target, like what happened over one step of this action, we're just going to correct for our distribution over that one step now. We're going to say, over that one step, I had some behavior policy that generated some action, and there's some probability that I would have taken that same action under my actual target policy I'm trying to learn about, and we just consider the ratio between those two things, and we multiply our target by those things, so that we weight how much we trust this target that we look at by how much our policy really matched what was actually taken in the environment. If these don't match at all, we can't consider this. This basically leads us to infinitesimally reject something or to take huge account of something. So you can still get high variance. We still increase the variance by importance sampling, and it can still blow up, but it's much, much better than Monte Carlo. Now, the idea which works best with off-policy learning is known as Q-learning. This is specific to TD0 now, to SASA 0, for example. And what we're going to do is consider a specific case where we're going to make use of our Q values. We're going to make use of the action values to help us do off-policy learning in a particularly efficient way that doesn't require importance sampling. And so the idea is very simple. The idea is we're going to select our next action using our behavior policy. Okay? But we're also going to consider some alternative successor action that we might have taken had we been following up our target policy. So we sample, this is our random variable representing the real thing we took in the world, that's time step t plus 1. And this a prime is like our alternate thing. Like we're just imagining, if I'd taken this thing under my target policy, what might the world have looked like? And now all we're going to do is we're going to update our Q value for the state we started in and the action that we actually took. We're going to say, well, the value of that state and that action that we actually took, we're going to update towards the value of our alternate action. So when we bootstrap from the value of our alternative action, because that's the thing that tells us how much value we'd actually have got under our target policy. Like when we sample from this guy, that tells you something about what really would have happened under our target policy. So it looks a bit like this. We now replace our SASA update, where we have our Q value for S and A being updated a little bit in the direction of the reward that I actually saw. So I was in this state, I took this action for real, even though it wasn't the one that I would do now. It doesn't matter, we're just asking how much value would I get if I took that action. I'm going to update it a little bit in the direction of the reward plus the discounted value of the next state of my alternate action under my target policy. This is what would have happened if I was really following the policy I care about. So this is a valid update. This is the Bellman equation again. It's completely valid. The Bellman equation for Q doesn't require us to importance sample. We're sampling that kind of Bellman equation. That's the idea of Q learning. Yeah.
Can you just be clear, like, which parts are from your behavior that you stored and which is online in that last equation?
Nothing is stored. I'm not sure. So, well, the Q
so
values
you're
are
sampling
stored.
AT plus 1 from...
So you're sampling AT plus 1 from your behavior policy, and you're sampling A prime from your target policy. So each time you get to a state, you're considering the thing you actually took, and you're also, that's generating your real behavior, the thing you actually took, and that's the trajectory you're actually following. But at every step, you're also considering some alternate action you might have taken, and that's the thing that you bootstrap from. You bootstrap from that Q value. Now, there's a special case of this, which is the well-known Q-learning algorithm. So if you hear about the Q-learning algorithm, essentially is what we're going to talk about in this slide. And it's a special case where the target policy is a greedy policy. So this is the special case where we're trying to learn about greedy behavior while we're following some exploratory behavior. And the special thing about Q learning is that both the behavior and the target policies can improve. We allow improvement steps to both of them. But what we're going to do is basically at every step, we're going to make the target policy greedy with respect to our value function. So we're going to ask about this deterministic thing, which really acts, as aggressive as possible. We're trying to learn aggressively about what we consider to be the best behavior given our Q values. But our behavior policy is going to be epsilon greedily. So our behavior policy is roughly going to follow sensible things to get us to good parts of the state space, but it's going to explore a little bit as well to make sure we get to new things as well. And when we plug this in to the previous slide, we basically end up seeing that, so this is the target that we had in the last slide, our R plus Q, the Q value of our alternate action. Our alternate action is this argmax, the greedy policy. So when we plug in this argmax, if you basically want to know what's the Q value of the argmax of your Q values, that's the same as the max of your Q values. So it's basically what Q learning does is it updates a little bit in the direction of the maximum Q value that you could take. So that looks like this. So we're just going to have one diagram to display this. This is the well-known Q learning algorithm. I call these SARSA max updates because you're looking at S, A, R, S prime, and then the max over your A primes. And what we're doing is we're maxing over these guys. We're updating our Q values a little bit in the direction of the best possible next Q value you could have after one step. That's the idea. So it should be familiar from the Bellman optimality equation. This is basically just like the Bellman optimality equation. And this algorithm, again, converges to the optimal action value function. And so it's a standard idea for reinforcement learning. So just to wrap up, I just want to bring out these relationships between these full width updates that we had in dynamic programming and what goes on in temporal difference learning. So in this column here, what we've got is a dynamic programming algorithm that we looked at in the previous lecture. On the right-hand column are these sample-based algorithms, TD and algorithms that we've looked at in the last lecture and this one. Okay, and so if you use the Bellman expectation equation, so this is which Bellman equation you use. If you use the Bellman expectation equation for the value function v, for the state value function, you can use dynamic programming to evaluate your current policy, or you can just sample this thing and take just one sample of this diagram by sampling from the environment and sampling from your policy, and that gave us TD learning. So these guys are just a sample of these guys. Wherever you've got an expectation here, you sample it to get your TD learning algorithm here, and that gives you your target. So the target for your TD learning algorithms are samples of the right-hand side of the Bellman equation. When we do the Bellman equation for Q pi, we can actually do SARSA now. So when we use the Bellman equation, the Bellman expectation equation for Q pi, we can use that to evaluate our Q values and then plug that into our generalized policy iteration to make our policies better and better and better. So we can either do that using a policy iteration framework for dynamic programming, or that gave us the SARSA algorithm. And then finally, we can use the Bellman optimality equation for Q star. And when you use the Bellman optimality equation, you can either plug that into value iteration